Welcome everyone to this mini webinar on building retuning or BRT. My name is Alana Colvin and I am an Energy and Environment Technical Advisor with PennTAP, and I will be hosting this presentation. The intent of this presentation is to introduce and briefly discuss how to combine energy efficiency strategies with preventative maintenance to achieve your energy saving goals at the lowest possible costs. In this mini webinar, I will introduce building retuning and its phases. We will discuss some investigation tools and some sample calculations. We will share some success stories and then finish up with a quick overview of PennTAP. The objective of this presentation is to provide you with a background introduction of BRT and provide information on cost-saving measures to effectively maximize the time we have during our workshop. So what is building retuning? Building retuning, or BRT, is a prescriptive approach to identify and correct low-cost, no-cost building operational problems that lead to energy waste. The principles of BRT are simple. If you don't need it, turn it off. If you do need it, run it efficiently. Your aim is to learn your building's personality so you can get the results you're looking for. Know where your occupants are and at what time of day. Take the time to adjust your controls on your energy-consuming systems to reflect your real needs. Also support continuous training, which will help in creating new positive behaviors. The combination of these principles will support your success in reaching your goals to reduce energy costs. There are 5 steps to BRT. Step 1 is data collection, tracking down what you have installed and related building information. This data will be useful when planning your walkthrough during the second step. Examples of data collection include the size, age, and type of your building, any meter information or utility bill information. Also consider the hours of various operations. Do you run any specialized hours, such as holidays or events? Do you have any HVAC zones? Consider their timing. Investigation or walkthrough is the second step. After you have the data collected, it's time to investigate. Look at all the building's conditions and operations. You want to investigate both during the heating season and the cooling season to see if everything is operating properly. You want to log all information and observations during the walkthrough. This will help you capture opportunities and ultimately calculate potential energy wastes and savings. The implementation step, this is self-defining. This is the application of your prescriptive retuning measures. Documentation, step 4. This is the reporting of your retuning findings and your impacts. Maybe you found some opportunities throughout your facility. Maybe it's for LED lighting, or you saw that you should insulate some of your hot water piping. You know what you need to do for implementation to fix the identified problems. Now you need to document and calculate what the savings would be. This will help you rank your projects so you can select which ones to pursue with going forward. After you have initiated the first steps of BRT and you have implemented some projects, your future goals will include continuous improvement and sustainability measures. We will discuss benchmarking and energy policies during the workshop. But reflecting back on the principles of BRT mentioned earlier, the sustain step is necessary to keep up with the positive impacts you've initiated so that you do not lose your momentum. While completing your investigation, which is step 2 of BRT, we recommend you take a few low-cost tools with you to help uncover any issues. The kilowatt is an electricity usage monitor. Connect appliances to the kilowatt and it will assess how efficient they are. The LCD display will count the consumption by kilowatt hour. From there, you can calculate your electrical expenses associated with that tool or equipment by day, week, month, or the entire year. You can check the quality of the power by monitoring the voltage, line frequency, and power factor. A light meter is used to measure the number of foot candles in a designated area. This is helpful to understand if the area is overlit, underlit, or if daylighting is effective. Distance meters, or a measuring tape, can be useful to confirm the square footage of a space, and you can use that information to size equipment, such as if you are considering ventless HVAC systems, among other projects. Many smart tools are available nowadays and are useful in building retuning to measure temperature, humidity, airflow, and air pressure. Find problems like air leaks, missing insulation, or even electrical overloads in power lines with the Seek Thermal Infrared Camera. This is a tiny, compact, portable camera, and this equipment can be used with either Android or iPhone smart devices. As you can see in the photos, we have used the infrared camera to see heat loss from uninsulated piping in the top left photo. In the center, you can see an interior door being used as an exterior door and is therefore lacking the proper insulation. In the bottom right photo, you can see a corner of the room has missing insulation. Granted, in this case, you would need to investigate more to determine the root cause, but at least you have discovered a problem and now you can move forward to correct it. There are a lot of high-cost infrared cameras out there, such as these, which cost thousands of dollars. But the basic model of the Seek thermal camera only costs $250, making it a low-cost tool. The blue devices seen here are AAB Smart HVAC Environmental Loggers. These connect to your smartphone through Bluetooth technology. Through the app's dashboard, you can set up your tools. Name the tool, set it to take a reading once an hour or once a day. You can use the sensor to pull and download data onto your smart device through Excel. And from there, you can plot the data, as you can see above on this screen. Data from 5 offices and a community area were collected over a few weeks. The results show us that the offices were able to stay within their temperature bounds in their HVAC zone, while the community area varied greatly. Now there's evidence to support a closer look at that common area. You can use these tools to help you identify if a room is actually too hot or too cold. Do you think you might have a leak in a damp area or spot? Maybe it's an old issue and it no longer applies. You can confirm with these tools if you have an active problem or a passive problem. These tools are no bigger than an egg. They are discreet and they are very simple to use. There are a variety of AAB Smart HVAC tools that support building investigation. Another tool is the airflow meter. Here you can measure the airflow of your overhead vents, air blowing under an external door that might have broken weather stripping, or from wall units in the classrooms or in hallways. When was the last time your wall units were cleaned of debris? This tool can help you figure out if your equipment is showing signs of degrading. Please note that we will have these tools and others at the workshop for review. To take advantage of the smart tools, you will need to download these apps to your smart device. Seek Thermal is the app for the infrared camera, and CPS Link is the app for the AAB HVAC smart tools. These apps can be found on the product's websites and are free to download. I recommend downloading the apps prior to the workshop so that you can take advantage of these tools at a closer look. Energy savings. The concept is easy to discuss, but can be tricky to calculate. Up next, I'm going to walk through a few examples on how to calculate energy and cost savings. Lighting. A school building has a standard fluorescent lighting system comprised of 34-watt T8 lights with a standard ballast in a 4-lamp troffer. It is proposed to install 4 18-watt T8 LEDs in the existing fixture with no ballast. Estimate the energy savings in dollars and the simple payback if the system operates for 4,000 hours per year and has 100 fixtures. The demand charge used in the calculations will be $10 per kilowatt, and the energy charge is 5 cents per kilowatt hour. Also, an installed LED fixture is $50. There's a lot of information in this scenario, but we're going to break it down with what facts we have, and we will go through the calculation over the next few slides. We are looking to determine the energy savings in dollars and the simple payback, which is the time it takes for you to pay off your investment so you can start using those savings for a new project. So to move forward with this problem, we will need to determine the energy and demand savings. From the problem, we know that the existing lighting, there are 100 fixtures. The lights are on for 4,000 hours per year. Each fixture has a ballast. Each fixture has 4 bulbs, and that these bulbs are T8, which consume 34 watts per bulb, and that we know the ballast impacts the energy consumption, which is also called ballast factor. So in total, an existing troffer with bulbs consumes 156 watts. We also know for the new LED fixtures, there are no ballast. There will be a 1-for-1 bulb replacement, which will be now 18 watts per bulb or 72 watts per fixture. We know that to install 4 new LED bulbs in each fixture costs $50. From the utility bills, you can see your demand charge and your energy charge. In this case, though, we are using $10 per kilowatt for the demand charge and 5 cents per kilowatt hour for the distribution energy charge. So as suggested, we will calculate the demand savings and the distribution savings. We will take the difference between the existing consumption and the LED consumption to find the difference. Multiply that by 100 fixtures, and you will have, in this case, 8,400 watts of demand savings or 8.4 kilowatts of demand savings. Take the kilowatts you are saving and multiply this by the time in hours you are running your equipment. 4,000 hours per year gets us 33,600 kilowatt hours per year in energy savings. To determine the cost savings associated with the demand and energy savings, we will need the values from the utility bills, in this case defined as $10 per kilowatt and 5 cents per kilowatt hour in our problem. To convert to LED, we are saving over $1,000 a year on our demand charges and over $1,500 a year on our distribution costs. Total savings comes to be at $2,500 per year. To determine the payback, you will need to take the costs of the new equipment, in this case 100 fixtures, $50 for each upgrade will equal $5,000 of implementation costs. Then divide that cost by your annual savings. In this case, we have a payback of just under 2 years. Note that 100 fixtures for a campus of buildings or a district could be a small percent of the total lights. So to change a whole facility, you will see much greater savings. Make sure with any improvement to check for any funding or rebate opportunities to help you with the implementation costs. Those will ultimately shorten your payback timeline as well. To tackle the lighting, walk through each classroom, utility room, hallway, office, specialty room, and count your fixtures and the number of bulbs in those fixtures. In this example, you can see that we have categorized each room with an overall area description, such as office and production. Apply the format to what meets your needs for your building. You can set up a table to calculate the lighting information based on the investigation walkthrough that you've completed. Here you can see how much your lighting is currently consuming annually. Once you have what currently exists in your building, you can prioritize which bulb project to tackle first by estimating the cost savings from replacing your existing bulbs with LED. Every bulb consumes energy differently. And maybe there's a strong behavior control in place to justify the priority of different lighting projects. Remember, you can determine the project payback just like we did in the example problem. Just take that example problem and scale it to as many or as few rooms you are looking to upgrade. This will give you the evidence that there are energy savings and cost-saving opportunities to consider, and allows you to present your case in a logical, well-thought-out order for the rest of the team to review. Compressed air is one of the most expensive sources of energy in a facility. I know not every facility has compressed air, but I have seen some facilities with compressed air in their technology education areas and in their maintenance buildings. Also, if you find yourself eventually working with compressed air, there is value in this discussion. The overall efficiency of a typical air compressor system can be as low as 10 to 15% if you are not careful. To calculate the cost of compressed air in your facility, use the formula stated here. Compressed air. A facility has a 200 horsepower compressor, which requires 215 bhp. This operates for 6,800 hours annually and is fully loaded 85% of the time, has motor efficiency of 95%, and is unloaded the rest of the time, 25% load, full load bhp, and motor efficiency of 90%. The aggregate electric rate is 5 cents per kilowatt hour. We are going to use this example provided and break it down. Here we can calculate the fully loaded and unloaded costs of the compressor as it's currently used. When fully loaded, the motor efficiency is at 95% and the machine is loaded 85% of the time during the year. Unloaded, the motor efficiency is 90%. And remember, if the machine is loaded for 85% of the time, then it's unloaded for 15% of the time. This comes to a yearly cost of over $50,000. Once you know your yearly costs, you can manipulate the equipment to lower cost and consumption. Maybe you can change the operation schedule. Also, check your system for leaks. Leaks will make the system work harder to maintain pressure, and ultimately, leaks are a complete waste of energy and money. One last problem I want to walk through is with boilers. This is a typical boiler setup. For boilers, the main energy savers are at the boiler, steam traps, and the pipes. Big energy savings can be achieved by properly monitoring, adjusting, and controlling boilers, steam traps, and the hot water pipes. Standard values for combustion efficiency of a boiler can be looked up based on the net stack temperature and the oxygen content. The net stack temperature is the difference between the temperature leaving the boiler in the exhaust and the temperature entering the boiler. The air entering the boiler is usually the air within the boiler room. The energy savings from an increase in the combustion efficiency are calculated by taking the difference between the proposed efficiency and the current efficiency. The difference is multiplied by the fuel usage for that year and a unit conversion to switch from volume, such as MCF or CCF, to energy, which is in million British thermal units, MMBTU. Here is an example of using this equation. The difference between the recommended efficiency and the current efficiency are multiplied by the fuel usage. Consider your fuel type, if it is in oil or natural gas or propane. In this case, we are using natural gas, 1,020 British thermal units per cubic foot. The value is then converted into million British thermal units. This gives you the energy delta of what you're currently using versus where you could be. So then you can determine your savings and decide if a tune-up is right for your equipment. Also, as applicable, find and fix steam leaks. Small steam leaks have big costs. With a 150 steam pressure and a 1/8 leak, a system pressure of has steam pressure of 75.8 psi, whereas a leak that is 3/8 has pressure of 682 psi. In costs, these leaks turn out to have high value, costing up to thousands of dollars each year. The point being, it's critical to be aware of any leaks and to maintain and properly implement energy measures. So just like we talked about fixing the leaks for steam pipes and what the savings could be for your facility, now let's talk about insulating the boiler return and feed lines. In this example above, the facility has no insulation on the return or feed lines. The photos illustrate the heat loss from the pipes. Those photos from the slide before are from an actual client who insulated their return and feed lines, and these are their results. They ended up insulating over 1,000 linear feet of steam pipes and now end up saving over $40,000 per year by this energy saving measure. The radiant heat loss from pipes depend on many characteristics of the piping, and there are softwares available to calculate the heat loss after the relevant data is entered. We recommend using these tools to help you with your energy saving measures. Once you have your data, you can manipulate it to see how you're doing and see if there's any seasonal changes that make sense. You can also see when you're hitting your peaks and to see if there's a way to control those spikes. This can be done with your utility bills as well as any readings off of your equipment that you've been managing. Please note that PennTAP will be providing notes and fact sheets during the workshop to help you through these different scenarios. If you have any questions about your equipment or system, please feel free to reach out to me and I can help you find a way to address that issue. Success stories. After you have put forth all of your efforts in discovering the information about your building, investigated for improvement opportunities, and initiated next steps on energy-saving projects, you will want to sustain this hard work. This can be done in many ways. Consider an energy management system for your facility, or continue to benchmark using Portfolio Manager and the Asset Score tool. Continue forward with preventative maintenance programs, such as eMate or SchoolDude. Upgrade your Energy Star-related devices and appliances. And, when you can, tell your story about the savings from your current BRT projects. This encourages behavior changes with occupants of the building and inspires department heads to fund future projects. With that in mind, I'd like to share a few stories about previous BRT attendees. Brittany, the Sustainability Coordinator for Erie County, selected the Erie County Department of Health building for evaluation. 4 other regional facilities also participated. Since completing this program, Brittany's team has subsequently initiated multiple energy conservation projects in the county's library, health department, county prison, public safety, county courthouse, and offices of children and youth buildings. These projects included lighting upgrades, new hot water boilers, variable frequency drive for motors, water efficiency upgrades to toilets, sinks, and showers, and installation of new chillers. In addition, equipment that was near end of its useful life was replaced. An energy service company, ESCO, is helping to coordinate these efforts. A total energy and cost savings are estimated to exceed $24,000 per year. Since the initial BRT inspection in 2014, Kevin, Director of Facilities for Hampton Township, has undertaken extensive repairs and renovations throughout the township, including installing a white roof on an additional township building to reduce the cooling costs, installing LED lighting in the sewage treatment plant, and replacing 500 horsepower motors with high-efficiency motors that have variable frequency drives for improved load balancing. Replacing a 1.5 million BTU boiler that was operating only at 60% efficiency with a new 97 high-efficiency boiler. 4-stage boiler to heat the township swimming pool as well. Hampton estimates the annual lighting energy savings of approximately $7,700 per year and motor-related savings of approximately $36,000 per year, and a 14% reduction in the amount of energy needed to heat the pool. And a quick overview of PennTAP and the programs we provide. The Pennsylvania Technical Assistance Program, PennTAP, is at Penn State and is a statewide technical assistance organization charged with supporting Pennsylvania businesses and anchor institutions, including manufacturers, municipalities, educational institutions, entrepreneurs, and economic development agencies. As a department within Penn State, PennTAP offers unique access to abundance of resources from one of the more premier universities in the country, including faculty, staff, and students. PennTAP can also provide clients with assistance from a rich network of government entities and private organizations. PennTAP focuses on helping Pennsylvania businesses through 2 primary areas of expertise: energy environment services and innovation services. Since being founded in 1965, we have delivered services and solutions to many Pennsylvania businesses and professionals, creating a legacy of documented economic impacts within the state and positive returns on investments to funding partners. In the past 10 years, PennTAP has worked with more than 3,700 organizations who have turned in a reported approximate $300 million in economic benefits and the creation or retention of more than 4,000 Pennsylvania jobs. Our mission is to engage, empower, and educate Pennsylvania organizations through technical assistance and Penn State expertise and resources. PennTAP has two pillars in which we offer our services. We have the Energy and Environment team that offers P2, E2 assessments, E3 assessments, and ENMS, Energy Management Systems, and building retuning. We offer innovation as well, which covers product and process improvement, the Learning Factory, student entrepreneurship, and has access to PSU faculty and university resources. I'd like to take a moment and acknowledge these resources used in parts of this presentation. And if there are any questions, please feel free to contact me via email or phone. Thank you for taking the time to learn more about building retuning and PennTAP. I look forward to the workshop. And to learn more about our programs, you can visit our website at penntap.psu.edu. Thank you so much.